Okay, for the charged ring, obviously that would look something like this. We're going to assume that it has an infinitesimal thickness. So this blue thing has no actual width. Okay, if you can imagine that. So this distance from here to here is 0. I know that's technically impossible, but we will be talking about the charged annulus as our last example, and that one has actual thickness. Okay, like somebody said, it looks kind of like a donut. But we'll save the annulus for last. Okay, so just imagine a ring itself infinitely thin. Since this already occupies a plane, let's say it's the xy plane, we don't want to use y for our distance from the ring. We will go straight up and we'll call this z again. So we've done this in the past. We'll call that direction the z direction. Okay, so this is the point we want to find the potential at. And so what we're going to do is draw a sample slice of charge. So here's a little tiny sliver of our ring. Can you guys see the black there? It's on the ring. I'll highlight it. So we have this little piece here. How far is that thing? Well, just draw a segment. We can always label it later, right? So that distance is very important. In our formula, v equals k integral of dq over r. That is our r. That is the distance between the charged object and the point of reference that we wish to study. Okay, and then there's also another r, but this r is a property of the ring itself. So it's actually this r down here. And the distance straight up, we will call that z, which seems logical. Okay, so we get this right triangle, and it looks like this. Z, R, little r. So little r is the longer segment. Kind of weird. Okay, so obviously the Pythagorean theorem holds true, and z squared plus big R squared is little r squared. So r can be replaced in our formula up above with little z squared plus big R squared. So that's going to go in at the bottom of our integral. dq, let's talk about dq, Dairy Queen. I want a Blizzard now. Hopefully you've had a Blizzard. They're delicious. If you like ice cream. What is dq? Well, dq is technically, since I've defined this as no thickness, just think of it as a length ds, and it has a relative, a uniform charge density, and we'll use the linear case, lambda. So remember we said that dq is always going to be either lambda times displacement, or it's going to be sigma times area, or it's going to be rho times slice of volume. We're not doing volume, we're not doing area. The closest thing we have here is distance. So we're doing like a little linear thing. Even though it's wrapped into a circle, it's more of a linear idea than anything. So we're going to use a lambda ds for our dq on top. Okay, it's time to rewrite the integral. Can I erase the green? Okay, I don't see any heads shaking or pencils rushing, so I think we're good. It's going to look like this. The voltage, the total potential, is going to be K and then lambda ds over square root of, and then we had z squared plus big R squared. Now here's the cool thing about this integral. It looks just as scary as the last time we wrote this. In fact, it looks almost exactly the same. Last time we pulled out the lambda because we didn't believe lambda should be changing as we wrap our way around the circle. Remember, you're going around this way. ds is going around this way. So we pulled the lambda out. But we had to leave everything else in last time. This time that's not true. As we rotate around the ring and we pick different sample charges, you'll notice something. Every sample charge we pick is still located capital R units towards the origin and z units up. In other words, z and r do not depend at all on which sample piece we pick around the ring. So some people call these elemental charges. I don't really like that name. I like to call them differential charges. These little differential charges, doesn't matter which one we pick, they're all the same z and r away from point P. So this time we're going to pull out everything. And it doesn't get any simpler than that. What's the integral of 1? Depends on the integration variable, right? The integral of 1 dx is x. The integral of 1 ds is s. So it's s. Now, we have to think of this as from s equals s initial to s final. So what's the final wraparound distance on a circle called? 2 pi r, circumference, right? So we're just going to wrap around the circle all the way around, adding up all the elemental charges on the ring. And so this becomes basically, this is silly, I'm going to write too much stuff again. Leading coefficient times s, we're going to plug in 0 and 2 pi r. And so here's what we end up with. Potential at any point on the z-axis is, and then okay, the charged disk is a very similar arrangement. The only difference is it's filled in with charge. So when you take your z distance up here, you have to understand that your elemental charge, your little differential piece, it's not actually a little segment. It's more like a ring of its own. So we take one of the rings out of here. So let's draw that thing. I like to call this a differential area, a dA, if you will. And since it is a bit of area, it does have a little thickness. We would say that if you times it by sigma, you should get your charge. So dq is sigma dA. And this is a little bit hard for students to understand, but hopefully it's just Calc 1 level, really. Since the distance around is 2 pi r, and the radius is r on the outside, and oh man, this is hard to draw. Let me draw it one more time. Give me a second. It's important that I draw a good one. I'm going to totally exaggerate. That thing looks like this, okay? And inside you have r, outside you have r plus dr, and then around you have 2 pi r, right? So if you take out some scissors and you cut this thing, right, snip, those don't look like scissors. Now they look kind of like scissors. Okay, you snip it, then you stretch it out straight like this. This is 2 pi r. It's now the length of the rectangle, and this distance is dr. So the gap between the rings was dr, and that is now showing up as the width of the strip. So I kind of unraveled it, But what's the area of this piece? Length times width, folks. What is it? Length is 2 pi r. Width is dr. See it? 2 pi r dr. That's the area of that little strip. So now I can erase my silly scissors and use that. We're going to times that by sigma to get our charge. So erase the scissors there. Erase my differential ring. Okay, so dq is sigma times 2 pi r dr. Okay, what am I going to use that for? Well, that's my numerator, right? So going back to the integral form of potential, and I sometimes forget that k out front. There we go. That's our numerator. That's our numerator. Okay, let's draw my disk again, and z is pointing straight up, and p is at the top, right? Okay, and then the slice we picked out is this red one, right? It has its own radius, r, and its own distance up, z, right? Okay, so it's such a bad drawing. One more try, sorry. This is the ring we picked. Here's our point at the top. And then I was going to draw those green segments again like I did last time. So this distance is very important. It's the distance to the ring. And that I'm going to need a new letter for. I can't use r like I did last time. We'll just call it d for distance, I guess. The little r is down at the bottom, and it does change from ring to ring. And this is z. So our Pythagorean theorem looks a little different this time. It's r squared plus z squared equals d squared, or d is the square root of r squared plus z squared. I'm not using capital R because this is one ring out of many rings that fit inside our big disk. You see? So I don't want to call it capital R yet. I'm going to save that for the radius of the whole disk. Kind of overwhelming, guys. I'm sorry. Trying to keep it simple. But okay, back to the integral now. Our integral should look like this. V equals k integral sigma 2 pi r dr all over square root of r squared plus z squared. And this one looks scary, but the 2 pi sigma can pull out. 2 pi sigma. And we just have r dr on top and square root of r squared plus z squared. And if you let u equal r squared plus z squared, then du will be 2r dr. In other words, 1/2 du is r dr. 1/2 du is r dr. Okay, so I'm going to go up here. I'm going to change that numerator to 1/2 du. And the bottom to simply rad u. Okay, I'm not done yet, but I circled it because I need to erase some things. Okay, so that was a u subintegral. Much easier than that horrible trig subintegral we did yesterday. Yesterday we didn't have an RDR on top, so that's why it was so nasty yesterday. Okay, back to, I'm going to erase this stuff again. Just the drawing and the Pythagorean theorem. And I'll pick up in the middle. So V is 2 pi sigma. Then there's a 1/2. So I guess the 2's are gone technically. Okay, and then we have basically integral of u to the minus half du. So we add a power, and now it's u to the positive half. Then we multiply by the reciprocal of the power, so that produces a 2 there. And there are limits of integration, so I'm going to do what I did yesterday. I put little dots here, and we'll come back to those limits later. Okay, and a student alerted me that I forgot my k, and that's on this step and this step. Thank you. And of course, up here. Okay, so anyway, we have to plug in our limits of integration, but these were originally r values. So we were studying a large disk. We had chosen a sample ring, a distance r from the center. So r needs to range from 0, which is the tiniest possible ring we could have picked, all the way to capital R, which is the biggest possible ring we could have picked. So we're picking a ring somewhere between 0 and big R. So little r is going to range from 0 all the way up to big R. Representing the little rings collecting like this to make a disk. R equals 0 is the littlest one, R equals R is the biggest one. Okay, then you just plug in the big R and the 0, and of course the 0 gives us nothing. So final answer is 2 pi sigma square root of capital R. And let me just check my answer. Actually, did I forget something? Oh, you know what? Mr. Soar's wrong. I plugged in R values. This is still a U, isn't it? This is still a U. I can't do that. Okay, Mr. Soar can't do that. I always get excited about plugging in the limits. I need to change the inside U back to what it was before. Remember, we said U was R squared plus Z squared? Oh, I forgot my K again, didn't I? Silly K. Okay, you're a special K. 2 pi K sigma. And then it was basically square root of U. But we have to change that back to square root of Z squared plus little r squared before we update these and plug them in. Okay, so that's what I did wrong. There we go. So it's 2 pi K sigma square root of Z squared plus big R squared minus square root of Z squared plus 0 squared. Okay, final answer, 2 pi K sigma square root of Z squared plus R squared minus Z. And we've seen this before where we have like a thingy-maboo out front and then a difference on the inside. We've seen that before. Now, because of all the Z's, you could do a gradient operator on this. You could use Cartesian, which is x, y, z. Remember, capital R is just a constant. Or you could use cylindrical coordinates on this one. And you actually get, it's actually, this, we've already done the charged disk field. So if you do a grad on this sucker, and you pick either cylindrical or Cartesian, and then you put a negative on it, you'll recover that same formula we had earlier in the year when we did the charged disk field. So you can negative grad this thing, and I just wouldn't pick spherical, because then phi is going to pop up. But either use Cartesian or cylindrical. They both have a z in them anyway. So that might be another thing to do another time. Okay, remember last time how we wrote it as total charge, big capital Q? That would be a little bit of a stretch on this one. So I would just leave the sigma there. Okay. And the last one's actually quite easy. Because the annulus is really just a portion of a disk. So imagine that disk, right? And remember we were picking rings in here. Well, when we did our integration, we went from 0 to capital R, and that gave us a whole disk. Why not just, instead of repeating the whole thing, just go right back to where we were a minute ago. What was it? 2 pi K sigma, right? And then we have square root of Z squared plus R squared. And instead of going from R equals, sorry, this should be a little r. Instead of going from R equals 0 to R equals big R, you're only going basically from R1, and then you're collecting your way out to R2, if that makes sense. So you're just going from R1 to R2. So you're not going all the way from 0 out because you're not going to fill in the middle. Or you could go from like A to B if you want to call it A and B. Those are like the radius of the inner and outer radius. Or you could, it's kind of weird, but remember in calc we called them little r and big R. Little r and big R when we did the washer method. Okay, so anyway, you plug them in, you get something like this. V equals 2 pi k sigma square root of z squared plus big R squared minus square root of z squared plus little r squared. Okay, so I've taken some of the sting out of the homework now. If you want to just reintegrate during the homework, I've gotten to where I can do some of these integrals, not all of them, but I can do some of these integrals in under a minute. So if you want to kind of rederive them when you're doing homework problems, that's fine. Or if you want to just go steal mine, just make sure you're using it in the right context, right? And again, on this problem, we are staying directly on the z-axis, right above the ring in the center. So, okay, so students suggested we just change these to R1 and R2, which is, I agree with that. I like that notation a little better. It's just radius outer and radius inner kind of idea. All right, so that concludes just finding potential of continuous charge distributions. And we picked one case where it's totally not symmetric. That was the charged rod. The other ones we were pretty much on the line of symmetry there. So.